let's continue the Pacheco's. So we stopped at the point where we had we discussed generation of the eta prime mass from the Toff determinant interaction. Okay, and so now let's try to sort of summarize the story from the point of view of different physicists, different observers, and see that everything matches. Okay. So as you remember, we had observers. It was Bob that was doing. So this was QCD scale. So we had Alice somewhere here. So we had ultraviolet observer, physicist, infrared physicist, and finally we discussed the story with how eta prime was generated through Toff determinant. Okay, so now let's see how these two observers see this phenomena. Okay. Now the setup. Let me remind you. We had QCD in which we had SUNC QCD, right, with a certain number of flavors, NF. We can even take NF equals 1 for this purpose. And we had, therefore, we wrote them in the left-handed basis. So these are psi j's and psi tilde j bars. So j and j bar are indices with respect to the, correspondingly, they get promoted into indices with respect to UN left and UN right groups, right? So that SUNF left and SUNF right. So this index, let's say, is J. This is, let's say, J bar. And then we have U1 axial, U1 vector, and U1 axial. And in this basis, U1 axial takes psi to, let's say, alpha psi, and psi tilde into I alpha psi tilde. Okay, so they're all left-handed. Of course, they transform in the opposite representation with respect to color group, the fundamental, anti-fundamental. So NC and NC bar, let's say. And they are bilinears with respect to the flavor group. Okay. And so now what we showed is that as a result of the generation of the Toff determinant, okay, the degree of freedom, which corresponds to the phase of the fermion determinant, okay, of the order parameter. So the phase the determinant condenses, okay, and the phase of this order parameter, because the term is generated, and so we call this order parameter phi, okay, which transforms as bifundamental with respect to SU NF SU left and right NF groups, right? And so in the effective Lagrangian, let me call it Toff Lagrangian, there is a term there is an effective in the effective potential that there is a term which is mod of expectation value of the determinant of all the fermions, right? Now, this is singled out by the fact that there is an anomaly-free subgroup, discrete Z and F, okay, which acts on phi as Z and F. And in the same time, this is what breaks explicitly U1 axial group, okay? And then this plus Hermitian conjugate plus And of course, this generates a potential of cosine type potential for eta prime. Okay. Now, of course, in principle, you can have higher order terms that depend on the determinant. Okay, they are not forbidden by anything. Okay. So, therefore, in general, if we could do a complete computation beyond the dilute gas approximation of instantons or whatever, we would recover some periodic function, not necessarily a cosine. Okay, but cosine comes from this first order indeterminate, if you want. Okay. So this generates mass for eta prime, but meanwhile, this also solves a strong CP problem. Okay. Because the quark flavors that we introduce are massless. Okay. Now, let's see how this story is seen by Alice and Bob. Okay. Now, for Alice is working with QCD Lagrangian, right? So it's some Lagrangian of QCD with let's say, okay. Okay, and then whatever field strength of QCD. Okay, let me call it F square. Okay, let me call it something else. Let me call QCD field strength as a mu nu, because F we are calling the three-form story, right? And there is a theta term also. Okay, now the theta term is in these notations would be AA dual. Okay, F mu nu, or in the language of our three-form notations, right, would be simply theta times F, where F, as you remember, F is as is this DC, F is epsilon alpha beta gamma delta, okay, D alpha C beta gamma delta, okay, or which is the same thing as AA dual, okay. Okay, so now, is everybody fine with these notations? What else? Yeah, nothing else there. So these are massless fermions, okay, fundamental, anti-fundamental. The color indices are not shown explicitly. Flavor indices are contracted. Okay. Now there is this theta term, which Alice can include in the Lagrangian, and as we discussed, this theta term basically is a declaration of a choice, okay, of the vacuum of one of the vacua of the theory. Okay. Now, without massless quarks, we discussed the story already. So theta is physical. Okay. With massless quarks, becomes unphysical. Now, Alice immediately can tell that theta should become unphysical. Why? Because Alice can get rid of theta by performing chiral transformation on the fermions. Okay. So, well, she knows that if she performs precisely this U1 chiral transformation, with U1 chiral transformation, the Lagrangian, because of anomaly, because of chiral anomaly, in the axial current gluon that we discussed yesterday, Lagrangian shifts by precisely term proportional to the theta term. okay, to theta-like terms. Okay. Now, of course, there is a coefficient, anomaly coefficient here, g squared divided by 32 pi's, etc., and number of flavors. I'm rescaling everything in my definition of AA dual, okay? But this overall coefficient, in fact, of course, is irrelevant because you can see that Alice can see that whatever is theta, she can always make a preemptive strike and eliminate it, okay? So therefore, theta cannot be physical, right? Okay, very good. Now, this, of course, matches fully the description in terms of generation of the top determinant, okay? Because the dynamics, the way this is realized dynamically, this story, is that we generate top determinant because of instantons, or because of whatever. At this point, it doesn't matter if it's only instantons or there is some additional contribution. The moment you generate top determinant in your effective potential, okay, effectively generate a potential for the combination that depends on theta and depends on eta prime. Eta prime is the phase degree of freedom of the quark determinant, okay? Now, this is the same combination, all right, that Alice can put in front of the AA dual by getting rid of the phase of the condensate, okay? Because we can always perform redefinition of the fermion fields, okay? Now pay attention. So there is a 3-level symmetry, global symmetry, okay? Now this global symmetry, of course, requires that A should be constant. The theory is not even invariant even under that global symmetry anymore because of anomaly, the rotation by the phase shifts the Lagrangian, okay? Now, you can perform an independent operation, which is field redefinition, okay? I can simply rotate my fields with alpha, which could be x-dependent, okay? This was never the symmetry of your theory to start with, obviously, okay? But it doesn't matter because the anomaly generates the similar shifts, okay, in the x-dependent story. And so, effectively, this gives you the universal story. The universal story is that every time there is a Goldstone boson of a symmetry that is anomalous, this Goldstone boson immediately couples to AA dual, okay? Universally. Okay, that's why also why Axiom couples to AA dual, okay? Okay, so then, therefore, this is the combination which appears in front of the AA dual, and then top determinant makes sure that these combinations acquires a potential, and so in the vacuum, this combination is 0, okay? So this, of course, this matches the anticipation by Alice that theta should be unphysical. Could not be otherwise, because it cannot be that in one language is unphysical and in the other language is physical, okay? So everything is fine, all right? Now let's see how this is seen. Yeah. This story is completely independent of the number of flavors. Of course, we don't want to, in general, we have to watch, because of completely different reasons, not to take too many flavors if we want to keep symmetry asymptotically free. Okay, but for this discussion, this is completely unimportant.
Okay, I think I'm missing an assumption because I know that in SU2 left, it's a chiral theory, so you can get rid of the theta term there. It doesn't exist. But I thought in SU3 it does exist.
I'm sorry. Which SU2 are we talking about?
Sorry?
Which SU2 are you talking about?
I'm talking about the standard model, so SU2 left. I know there's no like strong CP problem there because you can rotate it away into the measure, but
no, that's a completely different story. Okay, let's not confuse. Yeah, let me explain. No, I will explain it. Yeah. Now, if you want to ask a question, so this is a little bit disconnected from this story. Now, if you want to ask, so in the standard model, we have an electroweak symmetry group, okay? SU2 cross U1, all right? And now, you can ask this question, and plus the color, right? And here we have a theta term, okay, which is physical unless we introduce massless quarks, etc., okay, and or Accion. Now, if you are asking a question, why can't I write down a theta term here? Okay, all right, that's your question.
No, because I know you can. I know the calculation to show that you can't do it there because you can absorb it into the measure.
You can absorb because there is a baryon number symmetry in the standard model. In other words, in the standard model there is an unbroken baryon B plus L symmetry, and by doing B plus L transformation, you can get rid of the theta term. Even if SU2 were unhixed or whatever, because of B minus L symmetry, the theta term of SU2 left is unphysical. That's what happened. That's exactly the similar reason why this here is unphysical when it's a massless quark in QCD. So standard model for SU2 left behaves like QCD with massless quark with respect to its own theta term. Okay, because whenever there is a chiral symmetry, yeah, very good that you are bringing this up. So whenever there is a chiral symmetry which is unbroken, chiral symmetry which is only broken through the anomaly, whenever there is an anomalous chiral symmetry in your with respect to your group, okay, whatever this group, theta is unphysical because you can rotate it away. That's why theta is unphysical for SU2 left in the standard model. Now, on top of that, SU2 left is in the Higgs phase. And the story with instantons there is different. That's a separate story, okay? But this fact is independent of Higgsing. Standard model has, in other words, I don't know if everybody is following my answer, okay? No, nobody is following. All right, okay, I don't know. Look, the question was, okay, you follow the story here, right? What I said, because there is a chiral. So when I introduce massless quarks, right? There is this chiral symmetry. This chiral symmetry is a symmetry at the tree level, but it's broken by anomaly. What does it mean? This means that whenever I perform this transformation, the Lagrangian shifts by a term which is precisely has the structure of the theta term. Okay? All right? This is the fact brought by the anomaly. Okay? So this is chiral current, gluon. Okay? This anomaly makes sure that whenever I do this, I shift Lagrangian in this way. All right? Okay? So therefore, this tells me that whenever I have a symmetry that is anomalous, okay, the corresponding theta term is always unphysical. All right? Period. Right. Now, in QCD, to achieve such a symmetry, we need to introduce massless quarks. Okay, or an Axion or something else. Okay, we have to manufacture the symmetry. If quarks are massive, then we have to manufacture the model which delivers such a symmetry. Now the question was, what happens in this electroweak sector of the standard model? Electroweak sector has a non-abelian group, right? SU2 left. Okay, and naively I could have written down, not naively, but I can write it down, weak theta angle. That's what you are asking, right? Right.
I know that, but I like.
No, I don't understand that you know, but I'm explaining to others. Right. I mean, okay. So there is a field strength here. I don't know. Let's call it W dual. Okay. So therefore, I could have written this term. Okay. Now this term is unphysical because of the reason that in the standard model there is a symmetry B plus L, baryon plus lepton number symmetry, which is what? This is a symmetry by which I rotate all the quarks by, let's say, a phase, okay? And corresponding leptons, each quark color, and leptons I also rotate by the same phase, okay? No, this is B plus L symmetry. Now, this symmetry, okay, is anomalous with respect to SU2, okay? Right? Why? Because left-handed quarks, right-handed quarks I can forget for SU2, okay? Left-handed quarks and left-handed leptons, they transform under SU2, okay? Right? And therefore, if I run in the triangle where I have here SU2s, and here I have this current, B plus L, okay? So I have to run quarks and leptons. So there will be 3 quarks, okay, normalized in this way, this symmetry, 3 quark colors, and a lepton, right? Doublets. So there will be 4 doublets. Each of them have the same charge under this, the same sign of charge under this B plus L. Okay, so therefore anomaly is not cancelled. So because of this anomaly, okay, when I perform a B plus L transformation, the standard model Lagrangian, okay, shifts by a term which is proportional to. Okay, so then I'm neutralizing this, all right? Okay, so that's why in SU2 case, this is on top of the fact that SU2 is in the Higgs phase. So it's not like QCD. QCD is not Higgs in the standard model. SU2 is Higgs, okay? But this is on top of that, all right? So you are happy with this? Okay, so that's very good. So therefore, the massless quarks do exactly what B plus L does B plus L does for SU2. Now, notice here for B plus L, since this theory is chiral, okay, only left-handed components transform under B plus L, okay? So that's why we have this involvement of both quarks and leptons, okay? All right, let's come back to the QCD-like theory, okay? Okay, so in other words, the story with Alice is clear. Okay, so now the question is, how is this seen by Bob? This story. Okay. Because remember, what was the story with Bob? So Bob knew why this boundary term was physical. Okay, because he knew that there was a correlator. Q, right? So there was a topological susceptibility of the vacuum, right, which was a correlator AA tilde in the zero momentum limit, which is this correlator, okay, was constant, which meant that the correlator of the Chern-Simons tree form, right, CC at Q going to 0 had a pole at Q square equals 0, okay? So therefore, this was understanding of Bob that the theta term is physical because there is a boundary term, but there is a long-range correlator, okay, which couples to codimension 1 sources, and so therefore can bring information, okay, locally about the problem with the boundary term. Okay, so now somehow
those are the instantons, right?
Yes. So in other words, the underlying physical reason, you see, that's the power of this. This is what I'm trying to reiterate. This is the power of discussing in the language of topological susceptibility, because I could not care less what generates it. Okay, so it could be instantons, but could be also on top of instantons something else. By the way, there is a, okay, if I have time, maybe I'll comment on it. From large N story, there is an evidence that probably there is something else on top of instantons, at least in large N C. This, okay, okay, this is this story with large N story of eta prime mass by Witten and Veneziano. And but that's a separate story. But what I'm saying is that for me, for this discussion, since discussion is at the level of effective field theory, I want to precisely explore all the power of the effective field theory. And the power there is that I don't care what generates this correlator. The moment you tell me that it is generated, I know that there is a long-range correlator which makes theta physical. Okay? Right. But yes, this is the result of integrating out the instantons and possibly some other stuff. Now Alice is telling Bob that she has massless fermions, massless quarks, okay? And therefore, she made theta unphysical, okay? Now, how should Bob understand this statement? Okay, Bob should be able to translate this in his language, this statement, right? Now, the only possibility for Bob is that long-range correlator no longer exists in the theory. So the long-range correlator became short-range, okay? The meaning that the pole is no longer at Q square equals 0, got shifted, okay, by some value, All right? Now, indeed, we know that this is the case, also by explicit computations, okay, by Schiffman, Weinstein, et al., for instance, okay. We know that indeed the correlator in the limit of the massless quark vanishes, okay. I mean, I'm not aware of any computation of this correlator from the first principles. But what people have done, they have related it to the known quantities, okay, through pion decay constant and this kind of stuff, okay. So indeed we know, and we can take it for granted, and I will also take it, this will be also important ingredient, that indeed QCD confirms that when we once we introduce massless fermions in the theory, the correlator is no longer long range, okay. Very good. So now Bob knows that what happened is that when fermions were introduced in the ultraviolet theory, massless fermions, the low energy correlator became short range, okay. And now Bob wants to interpret this in his language, and his language is the language of gauge redundancy of F3 form. And as we said, this theory has to obey the rules of the game of gauge redundancy. You cannot just randomly change the Lagrangian. So therefore, what's the conclusion? The conclusion is that the only way and we know by now that only way to make, so what happened here is that 3 form became massive, okay, literally. So before we had a massless 3 form, and somehow 3 form acquired a mass, okay. But 3 form is a gauge field, which means that when it acquired a mass, this means that it entered the Higgs phase or the Procca phase. So now you see what happens. The moment I introduce massless quarks in the ultraviolet theory, in infrared theory, I'm Higgsing the 3 form, okay? Okay, any questions so far? Okay, so now, how should we Higgs the 3 form? We know by now that to Higgs the 3 form, we need a pseudoscalar. That we can write it in form of we can write it in form of B mu nu field, okay? Or we can write it as simply a pseudoscalar. Now, who is the pseudoscalar? Obviously, there is an obvious candidate who it is. Actually, it's the only candidate because it's the only one that has right transformation properties, is the eta prime, okay? Now, what happens? What is the effective Lagrangian of Bob? Effective Lagrangian of Bob is, as we said, right? So some k function, algebraic function of f, okay? F is, again, right? F is this. Some algebraic function of f plus high derivatives that are unimportant, again, they continue to be unimportant, plus interaction between eta prime and f. Where is this interaction? It's exactly the same interaction. We wrote it somewhere, right? Yeah, it's exactly the same interaction as generated through the anomaly, because that already Alice knows. Alice knows that eta prime couples to AA tilde correspondingly to f. Okay, so this anomaly generates coupling between eta prime and A tilde, which means that in Lagrangian of Bob, we have a coupling eta prime f eta f. And there is a kinetic term for eta prime. Let me put 1/2 here. Now, of course, here, I mean, there is a parameter f, the decaying constant, eta prime decay constant. This parameter, I cannot tell you what it is, okay, from the first principles, because this requires computation of the condensate, because this depends on the value of the condensates, etc., okay? Something of order QCD scale. Yeah?
I think it should be exactly a condensate.
Yeah, but the problem is that we don't know what exactly the condensate is. That's No, how to compute it, we don't know. From
This E theta prime
no, sure, of course. I mean, that absolutely, because it's a Goldstone boson. It would be a Goldstone boson without anomaly, and so it is coming from the condensate. But again, the power of this discussion is that I don't even need that information. Okay, as long as you tell me that there is some parameter, the decay constant. Okay, I don't have to even know what it is. All I have to know that some condensation took place around QCD scale. Okay. Right, so then from here what do we get? We get precisely that story that we got, that Alice got, okay? That, again, we integrate out. So we have K prime, d mu of, and then we have potential for eta prime, which is of F, and this shows the universality of the story, because this shows, right, as we discussed yesterday, that you don't even need to know what K prime is, as long as K prime is something, some algebraic function, non-singular, okay, right, such that this equation, when I integrate this, right, plus a constant, this equation, because this is a K prime, which is the algebraic equation with respect to this, right? This has a solution of F being some function. Okay? You are done, because the vacuum of the theory is always where F is equal to 0. Okay? Now, of course, we cannot compute K from the first principle. We can expand K for the small values. Okay, for the small values, we can expand K as F square. All right, plus higher terms. Now, but we can also go conversely. For instance, if you if you want, so first of all, what are we learning from here, right? We are learning from here the following thing, right? Let's say I solve and I plug it back here, right? And let's see. So I get the equation that eta prime plus 1 over f eta f as a function of eta prime is 0. Well, this simply means that this object, whatever is here, is simply a derivative of a potential for eta prime with respect to eta prime, right? It's the first derivative of the potential, right? Okay. Okay, so now this tells you that first, not just the vacuum of the theory, but actually any extremum will be CP conserving, because at every extremum of at eta prime potential, F vanishes. Okay. Now there is a theorem by Waffa and Witten who showed very nice general argument that so we said that in QCD we have theta vacua, right? And these theta vacua are physically inequivalent. They differ by amount of parity breaking, by CP violation, but they also differ by energies, by amount of the energies. Okay. Now, the lowest state, they showed that it's always theta equals 0. Okay. So in other words, the lowest among these different theta vacua, the lowest vacuum, is CP conserving. Okay. Now, the reason why, nevertheless, we call all of them vacua, because there are no transitions among them. So without Axion or without theta prime, it doesn't help that the lowest state is theta equals 0. Okay. Because there is no dynamical degree of freedom that could bring you from one to the other. Now eta prime became such a dynamical degree of freedom. Okay, that's another way of sort of this fully matches this theorem, okay, Wafa-Witten. But we learn even more that actually not just the lowest energy, but any extremum effectively corresponds to F equals 0, okay, of the eta prime potential. Okay. Any questions so far?
You say that this eta field is a requirement to in order to this super selection work, right? In order to get to this minimum, we have to have the.
You have, yeah. In other words, in one language. So you see, there are several languages, and they all meet. So there is a language of Alice that she is not thinking in terms of dynamical relaxation or anything like that. Okay, she is simply saying, okay, I have massless quarks. Period. I know that I have anomalous symmetry. I can do chiral transformation, and I can get rid of your theta. Therefore, don't bother me with your theta anymore because it cannot be possibly be physical. Okay. Now, there is another language of Toft instanton integrating our instanton. We generate Toft potential, and we see indeed that the potential that we generate for eta prime is indeed such that it relaxes this. Eta prime gives a degree of freedom. And there is third language by Bob, who just knows that there must be such degree of freedom just from gauge redundancy. Because Bob knows that the moment you introduce massless quarks, correlator became short range. The only way to make a gauge field massive is to put it in the Higgs phase or Proca phase. Okay? So this means that there is a Stuckelberg field floating around, Bob knows. Again, he may not care who this Stuckelberg field is, but there must be one.
In order to save the CP.
Not to say, even if you don't care about saying, this information that the correlator died is already enough for Bob. Bob may even not care about CP violation or whatever. He just knows his problem is physicality of boundary term. Okay, so Bob knows that when it's a boundary term, it's physical because he has a long range correlator. Then he understands why boundary term can affect local physics. Makes sense. Now, he knows that once quarks are introduced, this correlator, the pole got shifted, they became short range. Okay, then Bob says that the only possibility is to Higgs this three form. In the language of the three form theory, the only possibility to Higgs the three form, we need a pseudoscalar degree of freedom. This pseudoscalar degree of freedom should come from somewhere. And we know very nicely where it is coming from because eta prime is just there. Okay, so this is the point. So
in both Lagrangian, this theta is 0, right?
Yeah, in both Lagrangian theta, effectively theta is unphysical because in Alice's language it's unphysical, and which means that CP violation is 0. What is 0 is CP violation. Theta is unphysical, CP violation is 0. Okay.
This is also a main ingredient. If we didn't want to save the CP.
Yeah, it's a sort of, yeah, it's a main, it depends on your motivation. You see, here I'm not discussing motivation. I'm not saying that I am desperately trying to solve strong CP problem. I'm just trying, I'm an observer. I'm trying to see what is happening, what physics is happening, and what is the interpretation of this physics from different points of view. Now, then we see, of course, that this physics solves strong CP problem. Okay, obviously, because CP violation is no longer there. Okay, yeah.
Sorry, but in nature, so the quarks have mass. They are quite mass.
Of course, that's why I'm not discussing nature. I'm discussing massless quarks.
Okay, but this does not mess with this prediction by Bob of this eta prime. The fact that the quarks have mass in nature.
No, you mean you are asking phenomenologically, you are asking what will happen if quarks have mass?
Both.
Yeah, I mean, so far, absolutely, yeah. We showed it actually yesterday already, right? Remember, I showed you yesterday that what would be an effect of massive quarks. Now you are asking a question. You are going a little bit ahead of my lecture. So you are asking a question now. What would happen if quarks were massive? Okay, right. That's what you are asking. Absolutely, yes. If quarks were massive in all the three languages, the same story would happen. Okay. In the language of Alice, since quarks are massive, there is no longer a chiral symmetry at the tree level. So she has absolutely no argument to expect that she can get rid of theta by doing chiral transformation. Fine. In the Toft's language, again, there is an explicit breaking of symmetry by mass terms. So therefore, top determinant, because now in the Lagrangian you have explicit mass terms, right? Psi bar, okay? You have the whole mass matrix. Obviously, see, this is no longer the only term that controls where eta prime relaxes. And unless your theory is extremely carefully tuned, generically this eta prime would relax somewhere, okay? But it doesn't matter where it relaxes. It tells you that now theta is physical. Even if you are fortunate enough to happen to relax in CP conserving vacuum, that's not a generic situation. Okay, it just happened because of some fine tuning or something. Okay, right? And finally, the third language. And the third language I showed you already yesterday. Remember, we said that what would happen here is that now eta prime gets additional contribution from the mass to its mass, coming from the explicit breaking of U1 symmetry by quark masses. Okay? So therefore, there will be additional m square eta prime square. Okay? As soon as there is additional m square eta prime square, I showed you yesterday that now here, this is no longer the contribution. Okay, let me put half here. This is now eta prime equals 0. Now, when I integrate this out and I plug it back there, you can see immediately that in the vacuum, and we did it yesterday, so that's why I'm not repeating it. We saw that vacuum is no longer at f equals 0, okay? Which matches this, and of course matches Alice's expectations, okay? Absolutely correct. Now, precisely because quarks are massive, at least this is what our friends are telling us from Lattice and Lagrangian. Since all the quarks have Yukawa coupling constants in the standard model, there is no chiral symmetry, it seems, that we can use. That's why we need Axion. Okay, so Axion, we need Axion in order to solve the strong CP problem.
To shift F to 0.
Yeah, because you need additional degree of freedom. You see, for Bob, it's obvious why you need Axion. If quarks are massive, Bob understands that there is no Stugelberg field anymore. Okay? Stugelberg field is the field that only gets the mass by being eaten up by a corresponding gauge field. Okay? So if quarks are massive, there is no candidate for the Stugelberg field. The necessary condition is that when you switch off anomaly and when you switch off mixing with the 3 form, this field should be massless. But that's not the case with eta prime. Correspondingly, immediately Bob knows that we need a new degree of freedom, new pseudoscalar that would get mass from the 3 form by being eaten up by a 3 form. But this pseudoscalar has no candidate in the standard model. That's why we need to introduce physics beyond the standard model. We need to introduce the Axion. Okay? Okay, any questions so far? Yeah.
Since we add the mass, but we never speak about the interaction of quarks among each other, so that these terms you always avoid. I mean, there's a big reason to this, why we avoid this. It's all dynamics of the course, it doesn't affect all these things.
I don't understand what. So what's the question?
The Lagrangian,
Yeah, we have quarks. I had quarks. Sorry, I raised it. Yeah, we had that there. Quarks were interacting through gluons, and of course they exchange gluons, etc. So what is your?
Did we add this? I thought that we never.
I wrote the Lagrangian of the QCD there, right? I just arranged. I had massless quarks interacting with. How would otherwise I get anomaly in the universe? I mean, if quarks were free. No, of course, the interaction of quarks are colored, so they interact with QCD, obviously, right? No, absolutely. For this, it's absolutely crucial that quarks are colored, that fermions are colored. If I have pure glue, and on top of it I introduce a fermion that is not colored, for example, a lepton, that will not solve the strong CP problem of QCD. Yes.
How do I see that this thing that you're playing with the prime is the less than the prime?
Well, it looks like it, yeah. I mean, yeah. I mean, you need okay. I mean, historically, people didn't know that theta prime was the eta prime, right? Historically, what happened is that one of the Goldstone bosons was missing, okay? Because if I have SU3 breaking of U3 chiral symmetry, right? The number of Goldstone bosons should be 9, and there were only 8 candidates, right? And 1 was missing, right? So, and this was the problem of U1 axial. Now, then, after all these things, Toft showed that actually the missing one is theta prime, which is getting mass not only from the explicit breaking of chiral symmetry by quark masses, but also from the instantons through the anomaly, right? Now, so in other words, the way we know that now you can ask the following question. Of course, here I'm not discussing real QCD, I'm discussing SUNC color theory, okay? And I'm calling it eta prime because in real QCD, this would be eta prime. In other words, if this were SU3, okay, and if I would have three flavors, okay, let's say up, down, and whatever, strange, okay, then the would-be Goldstone boson that I'm denoting by eta prime would be the one which is diagonal. U dagger, D dagger, okay? So, the one that corresponds to the breaking of this generator. Identification of eta prime is simple in the limit of massless quarks. That's the one that corresponds to the generator of anomalous U1. And there is only one anomalous U1, okay? All right, so that's the rule. So, in the limit of massless quarks, there is one anomalous U1. Eta prime, what I call eta prime, is the Goldstone boson of that anomalous U1. All right?
And it comes from the trace of the flavor.
Yeah, this is the generator. This one. It acts like unity on everyone. This is the U1 anomalous is the one which is in basis, in which all the quarks are written in the left-handed basis, rotates the phases universally. Okay, so there is one transformation, universally rotates all the phases. Okay, you can always normalize generators in such a way that that's the one which is U1 anomalous. Okay, all right. And that, if I take n equals 3 and nf equals 3, and I take quarks to be lighter than QCD scale, or okay, not terribly heavy, that would match what a real eta prime meson. Okay, all right.
But also the eta prime means will have the same quantum numbers and the mass is way bigger than the eta.
Sorry?
So you can see that this is the eta prime, the actual eta prime that you see in experiment.
No, he understands. I mean, he was saying why if I understood correctly, your question was why am I calling this eta prime? That was your question, right?
Yeah.
Because I'm saying I'm calling this eta prime because I'm calling this eta prime because of the simple reason, because if I would take n equals 3, nc equals 3, and f equals 3, and quarks light enough, this would be the one that matches the real eta prime. That's why I'm calling it eta prime. Okay, right? Yeah.
Can scale theory generate more than one scale in dynamics?
Can what?
I mean the scale theory. Scale theory generates.
Scale-free theory.
Yeah.
Whether it can generate more than one scale dynamically by dimensional transmutation.
Yeah.
Well, that's an extremely interesting question. In principle, why not? I mean, a priori, the fact that theory is, in other words, yeah, you could have gauge theories in which you have extremely rich dynamics of phase transitions and quantum critical points, etc. So there are different. In other words, okay, let's be specific. Let's see what do we mean under generating the scale. The different scale, meaning there are theories of QCD-like in which there are many scales at which many different things are happening. Yes, this of course. For instance, even in supersymmetric theories, you can have an extremely rich moduli spaces or quantum moduli spaces, etc., etc. So yeah. Okay, and anything else? Yeah.
I don't know if my question makes sense, but in the scale of energy of electroweak symmetry restoration, what will happen? The quark is a massless?
You mean symmetry restoration at high temperature?
Yes.
No, that's an excellent question. The question is, at high temperature, I don't know if you had lectures on cosmology or something, but okay, so at high temperature, the standard model, if I put standard model in the thermal bath, okay, at high temperature, the Higgs expectation value goes to 0. Okay, so this means that in the early universe, presumably there was a phase transition where Higgs acquired an expectation value. Now, the question you are asking is, if I take that limit, high temperature limit, quarks are massless, right? Looks like they are massless, okay? Because Higgs expectation value vanishes, and so therefore, whether at high temperature I could solve the strong CP problem, and then cool down with the solved strong CP problem, right? No, that's an excellent question. The answer is no, because what is important is not whether quarks are massless or massive, but what is important whether there is a chiral symmetry in the theory. And the chiral symmetry is not broken by quark masses, it's broken by quark Yukawa coupling constants. Okay, you see, in the standard model, but the question is excellent, yeah. So in standard model, there is a single Higgs that generates masses for up and down quarks, okay? And there is Higgs generates mass for the up quarks, so I have UL, UR, okay? This, let's say, the neutral component, let's take, right? Or let's take Higgs doublet, doesn't matter. So I can take left-handed quark doublet, okay, QL bar, QL could be UDL, and UR, okay, plus Hermitian conjugate. And then the down quark is generated by Higgs conjugate times epsilon tensor, as you know, right? Epsilon tensor in SU2, QL bar, DR, right? And this creates so if both Yukawa coupling constants, GU and GD, are non-zero, there is no chiral symmetry, there is no global chiral symmetry anomalous left in the standard model. The only global symmetries here are baryon and lepton numbers. None of them is anomalous under QCD. Okay, so as we discussed, one of them is anomalous with respect to SU2, but that's a different story. Okay, so the chiral symmetry is broken by Yukawa coupling constants. So that's good that you are correcting me, because when I say massless quark, that's what I mean. Of course, there are no massless quarks in the universe because quarks are confined. Massless quark, I mean quark without pair Yukawa coupling constant. Yes, absolutely. Anything else? All right. So now with Axion, story is literally the same. Okay, literally the same. I don't know if I should erase anything. Let me erase this. So for Axion, let's say, so we have to introduce a field. Let me call it a Pacheco field, for instance. Okay. So by the way, as I said, what is important for the solution of the strong field problem, that you have a pseudoscalar degree of freedom which couples to AA dual, to FF dual. Okay. Now, this is what is important. Okay. It doesn't matter whether this field is a phase of a real scalar field that you can UV complete in a 3+1 dimensional theory or whatever, or it comes from string theory. Doesn't matter. What is important is that you have a pseudoscalar degree of freedom coupled to AA dual. Period. Okay. But one way to realize this in a normal renormalizable theory is Pacheco, to introduce a Pacheco field, right? So because this is historically how the solution was introduced, right? So you introduce Pacheco field, you couple it to quarks. Now I'm making a shortcut to a simplified model, of course, right? Because as you know, in original Pacheco scenario, you need the 2 Higgs doublets. Then the 2 Higgs doublets give the axion, which is sufficiently low scale. It's excluded experimentally, so we have to hide the axion. So we need some high scale field, etc., etc. But since I'm not discussing phenomenology, I just want to show the axiom point. So I have a field which couples, let's take a single quark, okay? Doesn't matter, okay? A theory with a single quark. We can write it, actually we can write in the same basis, okay? Left. And now there is a chiral symmetry. This theory continues to have chiral symmetry because the masses are not hard masses, but they come from the expectation value of the scalar field, okay? And so there is a symmetry, U1 Pacheco symmetry, under which phi goes to, let's say, exponent alpha, let's say twice alpha phi, and psi, tilde and psi, they rotate their phases by. Okay, so on fermions, it acts literally as anomalous as axial U1. Okay, the only difference now is that there is a scalar degree of freedom which compensates for this rotation. All right. Okay, so now we can do exactly the same thing. I can write down. Now there is a new degree of freedom in form of the phase of this object. And I can write it down. I can freeze its expectation, the modulus of this guy, because it acquires expectation value at some high scale. I'm skipping this thing because you have heard about it. Okay, just to get to the. And I can write it as a. And this is my axiom. Okay, degree of freedom. And now, U1 axial transformation. Okay, it would be a U1 axial transformation. Acts on a scalar. Okay, it touches the face of a scalar. Okay. Now, you can play with different regimes if you want. So, for instance, you can take a regime in which here is a coupling constant. Okay. Now, you can take a regime for instance, as an exercise in which you take G times F. So, G times Fa, right? This expectation value. This will be mass of the fermion, right? Okay. So now you can play different regimes. You can, for instance, take F very large, okay? Take F much larger than QCD scale. Of course, Axion is interesting because it comes from the sector which is much larger than QCD scale. But then you can say, the question is what you want to take G. You can take G, for instance, such that the fermion mass is way heavier than lambda QCD. This would give you sort of a heavy quark, okay, which is irrelevant at low energies. We can integrate it out right away. Or you can even take this case. And as an exercise, play around and see in which regime who is getting mass from whom, okay? Now, let me for simplicity take this regime because I still want to say a couple of words about gravity. Okay, in this regime, quarks are extremely heavy. We can integrate them out, and through the anomaly, you generate exactly this type of Lagrangian for Bob, except of beta prime, I will have here Axion. Okay, so the story just repeats itself. Okay, everywhere we should put Axion. Now, this I'm not putting because I don't want to break explicitly the Pacheco symmetry, but the rest follows, okay? So everywhere I can just replace again, this I'm not putting there, and so on, okay? Okay. So it's literally the same story, okay? So there is absolutely no difference. And as we understand that there should not be any qualitative difference because in other words, what we learned is that when quarks are massless, the axion is eta prime itself, okay? So massless quark case is one particular case of Pacheco mechanism when the role of the axion is taken by eta prime, okay? So if you have a coupling constant of, let's say, of up quark where 0, this would simply mean that axion has been discovered long ago, okay, experimentally. But since it's not 0, we need an additional axion. Okay, now let me say, yeah.
So added to this, there's still the normal Yukawa term with the.
No. Here I took a toy model in which I only have one quark. Okay, even more dramatic that he was asking. Only one quark in the universe and extremely heavy. Okay, that's it. But yes, if you want to do real model building, this you studied, right? I mean, there are several versions of hidden axion. So, for instance, this version could go under the. This would be a version of Kim, Weinstein, Schiffman, or this axion. Sorry if I forgot all the names. with normal quarks thrown, ignored, okay? Right? So this would be this version of that so-called heavy quark axion, okay?
You would add the Axion mass explicitly when you change.
Yeah, you see, this would exactly, it would precisely do that. Axion would never solve the strong CP, would not solve the strong CP problem anymore, okay? Right? And this is precisely the point. Now the question is, I want to move to this discussion about gravity, okay? Now the question is, okay, now with this discussion, for instance, right, we learned that we can introduce so let's ask the following question, okay? Now, the one worry about Axion solution of the strong CP problem that is floating around and people were discussing and taking seriously is gravity, okay? The problem with gravity. Because there is a question whether gravity could generate this contribution, okay? This to an axion mass. Okay, so in other words, gravity would generate a contribution into the axion mass, and if that's the case, if the contribution is too high, then the solution is ruined. Okay, right? Now and I want to discuss a couple of things because this way of understanding axion through the gauge as a gauge theory. Okay. On the other hand, what we have shown, right, during these lectures is that I can understand axion phenomena as a gauge phenomena, okay, as a Higgs phenomena. And now the question is, in that language, this language is more powerful because it's based on gauge redundancy. And we have more control of gravity in that language. That's one of the advantages of the gauge redundancy language, okay? Now let's first see what is the argument, standard argument. We call this argument Folk's theorems because it's hard to trace the origin, but the argument is beautiful. Okay, the argument comes from a general argument that gravity should not tolerate global symmetries. Okay, now and the argument is very elegant. Okay, so let me therefore discuss very briefly this Folk's theorem. Okay, why gravity should not tolerate global symmetries. Imagine that you have a global symmetry, okay? And this global symmetry is exact, so it's conserved, okay? Now, let's say, I don't know, it could be whatever symmetry. Let's say it could be baryon number or lepton number or whatever, okay? Now, let's try to prove that this cannot be case if we have Einstein gravity and one of the consequences of Einstein gravity are black holes. Okay, so let's prove that this is incompatible with the physics of black holes the way we know it. Okay. Now let's do the following thought experiment. Okay. So we have this U1 baryon number. So by the way, I'm a little bit improving on the original formulation of Folk's theorems. Okay, because it had sort of a loophole. I will even close that loophole, okay? Now, let me start the following thought experiment. I can prepare a huge black hole of unlimited mass, okay? So arbitrarily large black hole, right? Of certain mass, m, okay? And I can endow this black hole, therefore, since mass is not limited, right? I can endow this black hole with arbitrary baryon charge, okay? So let's say Q baryon. So there are different ways to do this, okay? First, you can bring together many baryons and collapse them into a black hole, or you can take a big black hole and throw in baryons, whatever you want, okay? Now, the thing is, okay, so now, imagine that baryon charge is conserved, okay? So then I have an observer, okay, let's say Alice, and Alice controls this amount of the baryon charge that went in, and then she controls the amount of the baryon charge that should come out when the black hole evaporates, okay? Now, what happens? Of course, we have to be extremely long-lived for this type of experiments, but that doesn't matter. So we have an eternal observer that is doing this experiment. Now, the two things are important. First, in black hole physics, we have so-called classical no-hair theorems. Now, the no-hair theorems are telling us that black holes cannot carry a quantum number. Black holes cannot have classical hair, meaning that they cannot be distinguished by performing any classical measurement outside of a black hole by the quantum numbers that are not sourcing massless gauge fields. Okay, so the quantum number has to be sourcing either spin 2 or spin 1 or something like that. Okay, so for example, if black hole has an electric charge, that's fine, we can control it. If black hole has spin, we can control it. Mass, of course, we can control, and so on. Okay, but there are only few quantum numbers of that type. Okay, so in other words, the quantum numbers that are not giving you Gaussian type integrals at infinity that you can measure at infinity, those quantum numbers are not revealed by a black hole. So from outside, you cannot tell whether a black hole has baryon number 10 or 1000. Okay, right? Okay, so this is fact of these are the extremely well understood facts about black holes. Okay, all right. Now there are some subtleties in black hole hairs when the black hole hair is like topological, Skyrmion type, or there are also black hole hairs which can be measured by Aronow-Bohm type experiments, etc., etc. Okay, very interesting stuff. But here we have a normal baryon number, no gauge fields involved, no topology. Although even with baryons there is this baryon-Skyrmion correspondence, which I don't want to enter there. Now, so what happens? So Alice waits. Now she waits and the radiation comes out. So black hole becomes smaller, radiating out, becomes even smaller, and finally evaporates. Okay, so now a black hole evaporates by Hawking radiation. And Hawking radiation in the limit, so Hawking radiation so the Hawking radiation has been computed by Hawking, right, in the limit in which the semi-classical approximation is exact. Okay, so what is that limit? If I have a black hole of mass m, this black hole has a corresponding gravitational radius, Schwarzschild radius, which is twice mg Newton. And now I can take a very smart limit in which mass goes to infinity, g Newton goes to 0, okay, but r is fixed. So you make gravity infinitely weak, you make black hole infinitely heavy, but you fixed geometry. Okay. Now in this limit, the computation can be done, that has been done by Hawking. And in this limit, of course, in this limit there is no back reaction on a black hole because black hole is like an infinite capacitor. Okay, so it radiates. Now it has a temperature. Black hole has a temperature in this limit, which goes as h bar over r. Right? Okay, let's put h bar 1. So 1 over r. Okay, so therefore, this usual story with black holes is it radiates in an approximately thermal spectrum. Okay. Now the deviations from thermality are extremely small. They are non-zero. Okay, but they are small. Now, how small? The parameter that controls deviation from thermality is the derivative of a temperature. Now, because black hole evaporates, there is a Stafford-Boltzmann law for a black hole. Sorry. Okay, so derivative of the mass is minus t square, and correspondingly you can form parameter which is t dot over t square. T dot is the time derivative of temperature, and as long as this parameter is much less than 1, the semi-classical approximation is perfect. Okay, so we can treat black hole as a thermal bath, approximately thermal bath. Now this approximation for standard Einsteinian black holes, okay, only breaks down around Planck temperatures. Okay. If you have more particle species, actually it breaks down earlier. Okay. But let's assume that we don't have like an infinite number of particle species. So in general, this approximation breaks down at the scale when black hole radius becomes less than the Planck length times this number from the species, okay, square root of species. All right. But okay, this is if number of species, we take the number of species of the standard model. This is not a dramatic improvement. Okay, so in other words, there is some fixed scale. Let me call this fixed scale L star. Okay, this bound. Let me call it L star. And as long as black hole is bigger than L star, it evaporates approximately thermally. Okay, all right. So now, what is the consequence that Alice can draw from here? So the consequence is that original baryon number cannot be revealed by a black hole because the evaporation is quasi-thermal. Quasi-thermal evaporation means that the chances to produce baryon and antibaryon are the same. Okay? So the thermal baths cannot distinguish between baryon and antibaryon. So therefore, if the initial baryon number was Q baryon, essentially you can estimate, it's easy, that all the way till this point, at best you produce order 1 baryon number. Okay? Not even that. Okay? Which means that, so now we got a problem, because this means that black hole is labeled by a conserved quantum charge, okay, but is not returning this quantum charge up until a fixed scale, okay, and this is a big problem. This is a big problem. Why is it a big problem? Because two conclusions: either this charge cannot be conserved, okay, then everything is fine. It's just not conserved. Okay, or you have to assume that at this scale you have infinite number of different species of black holes which are labeled by different charges. Okay? Now, theories with infinite number of species at any scale violate unitarity. Okay? Because you cannot have infinite number of species at a fixed scale, because then any process, like, I don't know, their contribution into any process would give you infinite rate, right? Okay, right? Because in whatever they contribute, they will contribute with the multiplicity. Okay, so therefore, the conclusion is that the global symmetry cannot be, global quantum numbers cannot be conserved by black holes. Okay, which means that they cannot be conserved in the theory. Okay, so by consistency, theory should include terms that violate those quantum numbers. Okay. Now, if we generalize this story to Axion, well, we'll say that, okay, but wait a minute. Then why am I saying that this global symmetry is exact? Okay, right? And this is considered to be one of the problems for Axion story. But now, you see, we have a very powerful tool. Now, the question is, I mean, can we say more without knowing precise UV completion theory of quantum gravity? Okay? Now, in the standard language, I don't know how to do it. But we have a more powerful language, because we have a language of gauge redundancy. And this language allows us to see how black holes could spoil the Axion solution of the strong C problem. Okay? And let me remaining. Can I have 5 minutes? Yeah. Or even 15. 15. I have 15. Sorry, I was also watching this clock. And all right, very good. Okay, and here, so to make this very very clean, let's take let's go to the gauge language as we discussed. Okay, and let's say Alice. Okay, so Alice now is solving a strong C problem in the standard model. Okay, and she says, okay, I can solve the strong C problem in purely gauge formulation. Okay, I don't want to hear anything about Pacheco global symmetry. For me, the symmetry is not a global symmetry. For me, it's a gauge symmetry. Okay, so Alice introduces a field B mu nu. Okay, And then she just simply constructs the Lagrangian, okay? Couples this B mu nu in a gauge redundant way, to a QCD 3 form, okay? And as we know, this coupling is unique. It's fully fixed by gauge redundancy. So therefore, we have Lagrangian of Bob, right, was there with the QCD. But now Alice adds this coupling to B mu nu, right? So now we have F. Let's take F square for simplicity, this K function to be F. And then Alice adds a coupling of B mu nu to a 3 form. Okay? The one that we discussed. So this coupling has the following form. I mean, C minus DB square. Okay? Now, this coupling is fully fixed by gauge redundancy, as we showed, right? If we dualize this theory, we get this the old Lagrangian. Sorry, let's call this Alice, and we'll get Lagrangian of Bob by dualizing this. I'm sure all of you did this exercise. AF. Okay, just not to carry indices around. Now, indices, everybody understand the indices, right? So this is 3 anti-symmetric indices here, index here, okay? Right? Or should I write it? Yeah, let's write it then. What's the problem? Okay. All right, and so if we dualize, we get this Bob, Lagrangian of Bob, right? And then now, Bob, because Bob thinks in terms of a pseudoscalar, Bob says, oh, but wait a minute, maybe gravity will break my shift symmetry and will generate a term of this form, okay? Now, but Alice is staying in her formulation, okay, of solution of the strong sweep problem. And now, what could be a counterpart of this in Alice's formulation? Right? So, let's see, right? Now, what was this term doing in this formulation? This term was unhixing the F, right? F form. Because without this term, F would be 0, space problem, right? So remember, so without that term, yesterday we wrote it, so let me not repeat it. So with this term, F is no longer 0, right? Because in the equation of motion for A, we have F, but we also have M square A. And the equation of motion for A, for F, we have A, and then when we solve for F, is A plus theta, and I plug it here, this constant part of the electric field is no longer 0 because A had a mass term, okay, different mass term. So if we take it and plug it there, we see that the vacuum was at A being 1 minus 1 plus M square, right? Something like that. Of theta. Okay, correct, right? Yeah, that's right. Right. So and okay. So what this means that the field F, because theta is the constant part of F, right? It means that the electric field got unscreened or got unhixed. So this means that there is an unhixing of a 3 form. Okay? Now, what's the counterpart here? Can I imagine writing anything which is gauge redundant and gauge invariant, which would have the same effect? Huh?
Something with gravity.
Very good. Something with gravity. What with gravity? That's the question. Must be something gauge invariant, something with gravity. That's already we are in a very good track. Ricci should involve maybe Ricci tensor. We'll get there. But what should be the physical effect? The best thing is to see what we are looking for. We are looking for the unhixing of the field, right? Now, how can I?
We should include some terms that give this, right? So
Yeah, that's correct. But
like in the previous example, we were including some mass term for each of the.
yeah, but it's something that would effectively generate a mass term. But let's go a simpler route, okay? In other words, we need a physical effect. Yeah, we need a physical effect the following. We had a gauge field that was screened, and now it was hixed, and now we want to unhix it. Okay? How can we unhix a gauge field? Now, the only possibility to unhix a gauge field is, why was gauge field in the Higgs phase? Because it had a Stuckelberg that was eating up. Okay? Now, the only possibility to unhix the gauge field is to introduce another gauge field which competes for the same Stuckelberg. Okay? Then the two gauge fields, they cannot share the same Stuckelberg. One combination will be unhixed. This is the only possibility, only gauge invariant possibility, which means that this immediately fixes what should be the story. The story should be that there must be additional free form appearing out of somewhere gravitationally, okay? In other words, instead of this, we should have an additional free form, okay? Let me call it free form of gravity. Let me call it G, okay? G. Or okay, let me call it like that, not to.
Proportion to R squared, the square of the Ricci tensor.
Yeah, I'll explain in a moment, in a microsecond. It involves Ricci tensor, yes. But yeah, it's RR dual. It comes from the RR dual. RR dual, exactly. All right. Now, we need a three form that comes from gravity. Then of course notice what happens, right? So we need another three form that will participate in this. Okay, let's write it now properly. Another three form with a different coefficient entering, but this is not important, the coefficient at the moment. So another three form, let me call it three form of gravity, plus the alpha b gamma beta gamma, okay, squared, okay. So here could be some coefficients, some relative coefficients, okay, some I, that doesn't matter. Now, and of course there must be the analogous form for this three form, obviously gravitational. So Fg square. Now you see what is happening. Immediately we can see what's happening. What is happening is then, now there is only one Stuckelberg, okay, that is shared by two gauge fields, okay, which means that you cannot make both massive. That's impossible. You cannot give mass to both. Why? Because you can immediately see that there is one combination only that is entering, okay. So in other words, there will be one combination which we can call what do you want it to call? Something like okay, let's call it I don't really have enough C what? C prime, very good, okay. That's good. Very good. This is C prime, okay? Excellent. So we have C prime, all right? And C prime becomes massive, right? And the orthogonal combination, right? So now we have two forms. So we have C prime, which is C plus C gravity. We can divide by square root to normalize, and we'll have another one. Presumably we should call it C double prime, right? Which will be C minus C gravity square root of 2, okay? All right? So one combination. So of course, if there are coefficients here in general, there will be like a Weinberg, like weak angle, right? The Weinberg angle, they mix, just like in the standard model, like Z boson and like the third component of the SU2 and hypercharge, they mix. Here also, these two people mix. And And C prime is simply a massless tree form. Okay? Now, therefore, in C prime, they both participate. And so that's the end of the story. In other words, the strong CP problem is ruined. I mean, the solution. Because now the Stuckelberg B can only give mass to one C prime, one combination. But there is an orthogonal combination in which QCD3 form participates. Okay? And we are back to the problem. Okay, so this is the only possibility. But now we should see how gravity can provide this kind of tree form. What is the form? Okay? Actually, there is a unique candidate in gravity. Now, and the story goes very closely to gauge theory stories. Okay? First, let me tell you. So that's candidate. This G. C of G. This is again a Chern-Simons tree form, but gravitational version of it. Okay? Chern-Simons tree form gravitational version is exactly the same way you use connection instead of gauge field matrix, right? Yeah. Okay. So this is anti-symmetrized, of course. So I'm only showing the second index explicitly. The other indices are contracted because Christoffel symbol has 3 indices, right? So the 2 are contracted, and the 1 is shown explicitly. Okay. All right. So there is this gravitational Chern-Simons free form. Okay. Correspondingly, there is a corresponding field strength, which is again D of anti-symmetrized beta gamma delta, which we can call F gravity. And by the way, check this, okay, obviously I'm out of time, that this is famous RR dual term. This is your Riemann tensor, and it's dual. Okay, so now this story fully matches the thing also in gravitational anomalies. Now, on top of gauge anomalies, okay, we can have gravitational anomalies. Okay, so in other words, in the presence of fermions, when we do chiral transformations, okay, the certain chiral transformations of fermions generate a shift of the Lagrangian also by something proportional to RR dual. Okay. So the story is now gravitational anomalies are very beautiful subject. Okay. There is a okay. There are reviews, but you can look up the paper by Alvarez Gomez and Witten, which discusses gravitational anomalies. I mean, there are, of course, more recent reviews. But in any case, okay, the point is that the chiral transformation, for instance, axial QCD axial symmetry, as a matter of fact, is anomalous with respect to gravity. So when we do chiral transformation, in fact, the Lagrangian also shifts by, not just by AA dual, okay, of QCD, but also shifts by this object of gravity. Okay, and that also matches. That also tells us that we are on the right track. So in other words, Pacheco symmetry is also anomalous with respect to gravity. Okay, this very naturally is telling you that indeed the form that could ruin the solution of the strong CP problem, okay, is the gravitational Chern-Simons. Okay, so now, what is the question remaining? The question remaining is, fine, you can tell me, all right, we shift with this, but so what? I mean, how do I know? This is a boundary term, again, right? So this is a boundary term. This is a gravitational version of theta term. But how do you know that this is physical? That's what you should tell me, okay? Okay, well, I don't know. We don't know. All right. So in other words, the fate of the axion, whether axion can be ruined in this gauge formulation, which is very powerful, whether axion can be ruined by gravity, hangs on physicality of this object. Physicality of this object without axion. Okay? In other words, the question is whether in gravity we have the analogous topological susceptibility. Just 1 microsecond. What is this? Yeah.
So basically what you still have to know the UV completion of gravity.
Well, not necessarily, because so one possibility could be that you could have objects which are not UV completion. UV completion happens above certain scale where gravity becomes strong. Okay. Now, we could have objects which are describable in the weak gravity regime. Okay. Weak gravity, I mean weak curvature regime. Okay. That could contribute here. Okay. So, for example, if you can find some trustable wormhole solutions, okay, wormhole type solutions, or gravitational type instantons, etc., then that would contribute here, okay. Okay, then this could answer the question, okay. So therefore the question is, if in the absence of massless fermions and axions, I have in gravity the similar story that I have in QCD, where topological susceptibility is non-zero. Now, gravitational instantons, they have been classified, okay? And in that direction, it doesn't look very promising that you can get on Minkowski space. Yeah.
So, if that thing is physical, then axions can't solve the strong CP.
No, let's not hurry. Then we'll see what should be then you have to worry, but it doesn't mean that the axion is ruined, because if it's unphysical, we are safe.
Then
we can go home. Yes, if it's unphysical, then from standard model plus gravity, okay, there is no evidence of the problem, okay? Of course, you can always create a problem if you want, introduced by whatever other. For instance, somebody can come and say, okay, I want to introduce some new 3-form because my theory has this type of new 3-form. For instance, this new 3-form could come from another gauge group, right? So imagine I introduce a carbon copy of the standard model, okay, right? And I say, okay, I have strong CP problem here, strong CP problem there, all right? And try to relate by symmetry these two groups. And naively, it looks like that one axion can solve both problems. Well, this shows you that one axion cannot solve two strong CP problems. Okay, one axion can only can only Higgs one combination. Now the thing is that you see that's a little bit departed a little bit, but theta is a choice of the vacuum. Since it's a choice of the vacuum, you cannot reinforce it by a symmetry. Because you see, if I have standard model copy and I have a hidden copy, right? Let's say Bob lives here, Alice lives there, right? Bob has one theta vacuum, Alice has another theta vacuum. And now we require that the theories are symmetric. But the fact that theories are symmetric doesn't mean that Bob has to choose exactly the same theta that Alice chooses, right? There is no reason for it. In other words, there will be some theta of Alice and theta of Bob. And the symmetry among the theories doesn't tell you that this choice should be symmetric. It only tells you that for every choice, theta Alice, theta Bob, there will be a symmetric choice, theta Bob, theta Alice. That's sure. Okay, there will be physically equivalent situation when Alice chooses, let's say, theta equals 5, or whatever. Bob chooses whatever, okay, and the vice versa. Right? Anyway, so this is related with that. Now, okay, so I don't know. I think that the promising candidates for this are micro black holes. Okay, for instance, for me, the promising candidates of this would be micro black holes. In other words, somehow saturating this correlator by micro black hole and summing over all this. Sorry, summing over all these micro black hole states. Is one direction, okay, we can think, okay, whether this correlator is non-zero. Okay, so let me finish with the final statement. Now, what if this correlator is non-zero? okay, if this correlator in pure gravity is non-zero, pure gravity, I mean gravity without axions and fermions, then we have to worry. But there is one avenue that we can take. What is this avenue? This avenue is, okay, if gravity gives another 3 form, let us introduce another axion. Actually, we don't need another axion. A light fermion would be enough. Because, you don't even need a light quark. Because we only need a fermion that has chiral symmetry with gravitational anomaly. We have such fermions, neutrinos. Okay? So in principle, neutrinos could protect axion from gravity in that situation. Okay? All right, so let me finish here. Then it becomes a matter of model building. I don't know, and of course, if you any questions, I'm happy to answer. Yeah.
Yeah, just a comment concerning the R alternative thing here. So if you have chiral gravitational waves,
Yeah, excellent.
the expectation value of R alternative becomes non-zero. So I don't know about the correlator, but at least then you get an expectation value.
Yeah, in other words, yeah. So if you have, but for that you need to introduce a new pseudoscalar that is there, right? It's not in pure gravity. Unfortunately, in pure gravity, you see, in pure gravity, for this to have a physical effect, to be locally measurable, we need somehow this correlator to be non-zero. So yes, if we introduce for instance, by the way, this kind of story game, let's say if neutrinos, imagine that neutrinos are the ones that protect axion, okay, from gravity. Then this means that neutrinos effectively mix with RR dual. And in that case, neutrino should deliver some kind of an effective pseudoscalar, degree of freedom, which would participate in gravitational waves. And then, yes, in that case, you can have this, you can have observable effects, because that would be a prediction for this. You see, if neutrinos protect gravity, this means that neutrinos then mix with RR dual, and so correspondingly, they should contribute into the gravitational waves. Yeah, absolutely. Yeah, gravitational waves would be one place where to look for these signatures of this kind of physics. Yeah, and that's very exciting. Yes, absolutely. Yeah. Yeah.
So the thought experiment that you gave of gravity violating the global symmetry, it was very limited to black holes. So should we expect that other than black holes, gravity respects global symmetry?
No. A black hole was a tool to prove in the quotation marks, because the black hole was a tool to prove that global symmetry is inconsistent, which means that to make it consistent, you have to include in your Lagrangian terms that explicitly violate it. Okay? So after that, it's not that global symmetry is only broken near black holes. No. Black holes was a way to set up an experiment which shows that in theory, this charge cannot be conserved. Okay? So this is the way you have to understand it. So black hole is like a way to smell that the fundamental theory somehow should violate these symmetries by some operators. Okay? Now, of course, you are absolutely right. This relies on the fact that we understand black holes. So this relies on the fact that the Hawking radiation we understand approximately. We don't have to understand it completely. So the quantum corrections to Hawking radiation, as long as they are small, this argument is good. Now, of course, if it happens that you have a theory of gravity where black holes have different properties, then of course the story you have to reconsider it. Okay, but I mean all these things are extremely rigorous within Einstein gravity. Okay, so if we are not questioning Einstein gravity at those distances, which I'm not, then yes, this argument is pretty instructive. Yeah. Okay.
No more urgent questions.
Okay.
We still have lunch.
Sure.